Hello, everyone. My name is Xinjian Li, and I am currently a postdoc at Computational Biology Department at Carnegie Mellon University, supervised by Dr. Min Xu. I'm very glad to introduce our work presented in AAAI 2022 on behalf of all the authors. The title of our work is Deep Active Learning with Noise Stability. Our work is motivated by a popular idea named noise stability. It has been widely used to improve model training, especially for deep neural networks. For example, in supervised learning, we usually apply some random noise or transformation on the original image, and then enforce the model to predict the same result. By this way, the learned model will be robust to various data perturbations. Here for active learning, we adopt a similar idea, but we swap the role of data and model. That means we aim to distinguish which data instance is more robust or sensitive to the model perturbations. Then we use this degree of sensitivity as a metric of uncertainty based on the current model. So when we apply a slight perturbation on the model parameters, if the prediction of an image changes a lot, it indicates a low confidence of this image. You can imagine that if the model is retrained with another random seed and converged to a different parameter, the prediction of this image will be probably changed. So in active learning, we tend to select this kind of hard instances for annotation. That's the basic idea of using noise stability to measure data uncertainty. This idea of noise stability has another natural advantage. That is, given a model noise, the output deviation also has a direction. Then this direction can be used to select a batch of hard instances with diverse sensitive features. For example, if a model perturbation affects the recognition of long ears, the representation of a rabbit image will tend to move to a bear image. Similarly, if the recognition of fins is affected, a dolphin representation may move to a whale. So by considering the diversity of the output deviations, the selected examples can cover more sensitive features to improve the future model. Based on those ideas, we have the following implementation of our algorithm. Here, we denote by Z the output of a data instance given the current model. It can be either the final prediction or a deep representation. Then we apply a small Gaussian noise to the model parameter and get the output deviation data Z. A normalization term is used here only for the ease of theoretical analysis. Then we repeat the random process by k times and generate k different deviations. Then we concatenate those vectors together to form the final output vector for each instance. Given the vectors for all the candidate instances, we adopt the k-means plus seeding algorithm for the subset selection. This step follows the same idea of the previous method page published in ICLR. The basic idea of this algorithm is, given a new candidate instance, we calculate the minimum distance with existing points. If this distance is larger, we will have a higher chance to choose this candidate. By using this algorithm, we are likely to select a batch of points with different directions and also larger magnitudes. Next, I will present some theoretical analysis of our method. If we apply the first order Taylor expansion on the output deviation delta Z, we will derive a form of projected gradient. Specifically, we get the Jacobian matrix J times a random direction U. We indicate this connection because gradient-based methods have been well studied in active learning. For example, the L2 norm of gradient has been widely used to measure data uncertainty when using a simple neural network. But we know that many modern deep models have a very huge number of parameters. So it's impractical to utilize its directions due to its extremely high dimension. So here we have the low-dimensional projected gradient as a surrogate of the original gradient. By our theoretical analysis, we can derive that our projected gradient has the same expected magnitude with the original gradient. And we also have two distinct properties in terms of the direction. That is, the projected gradients retain the same spatial relationship between two instances compared with the original gradients. This applies to the Euclidean distance and the inner product, which are commonly adopted to ensure diversity in active learning. While the previous analysis guarantees the equivalence between the original and projected gradients in terms of the expectation, we also care about how close between them given a limited number of samplings. So we also conducted the concentration analysis. And the basic conclusion is that we don't need a large K, that is the number of samplings, to get close to the expected value, because the convergence speed is indirectly proportional to log of n, where n is the number of candidates. Here is a whole implementation of our active learning algorithm with noise stability. We conducted some experiments to evaluate the performance of our method. The first group is image classification. We find noise stability is always among the most competitive algorithms on the three benchmarks. Here we use three different architectures, which are simple CNN, VGG, and ResNet, respectively. And our method is also applicable to different tasks, including regression on tabular data, image segmentation, and natural language processing. Some of the existing algorithms are not feasible for every task. For example, the entropy-based methods cannot be used for regression tasks. So our method has the additional advantages of model agnostic and data agnostic. And last, I would like to introduce an interesting ablation study. It aims to evaluate the individual contribution of the two factors in our algorithm, which is the magnitude denoted by M and the direction denoted by D. First, we observe that if we use the direction alone, it performs almost the same to random selection. This is consistent to our experience that random selection is very good to ensure diversity. But when combined with the magnitude part, the whole algorithm performs clearly better than using the magnitude alone. So this observation implies that utilizing the noise direction helps us to reduce the potential bias introduced by uncertainty-based selection. Okay, that's all the presentation. Thank you for listening.